Hey friends, in today's video we're going to talk about the different types of chemical reactions. Knowing these different types can help us to recognize patterns that we see in chemical reactions. And in doing so, we can even predict products. So stick around. The first type of reaction we'll talk about is what we call a synthesis reaction. In a synthesis reaction, we have two or more substances that combine to form a single product. A generic example of this is shown: A plus X yields AX. So the two substances, A and X, come together to form a single product. We'll call it AX. Here's an example of a synthesis reaction. We have sulfur dioxide that combines with oxygen gas to form sulfur trioxide. You can see how you have the two substances that come together to form one product. Here's an example of a synthesis reaction. Calcium oxide, when combined with water, yields calcium hydroxide. This is a beaker filled with ordinary water. It also contains an indicator. An indicator is something that we use to detect the presence of an acid or a base. In this case, when I add the calcium oxide to the water, it's going to combine to form calcium hydroxide, which is a base. The base will then make the indicator turn a bluish color. So again, here we have an example of a synthesis reaction. The combination of calcium oxide and water to form calcium hydroxide. The second type of reaction we'll talk about is a combustion reaction. In a combustion reaction, you'll have oxygen combining with a substance, and in the process, a releasing of energy in the form of heat and light. As a matter of fact, that last reaction, the one with sulfur dioxide and oxygen, could also be classified as a combustion reaction because oxygen is involved as one of the reactants, and heat and light energy are given off in the process. Here's another combustion reaction. The burning of coal or carbon in oxygen releases carbon dioxide. You can see how we have the two elements coming together to form the one product. Now you might be thinking, Mr. Risley, those last two reactions were also synthesis reactions, weren't they? And they are, but not all combustion reactions are synthesis reactions. Let me show you an example of one that's not a synthesis reaction. To the fume hood! Here's an example of a combustion reaction. When we add just a little bit of energy in the form of the striker, the propane combines with the oxygen to form carbon dioxide and water. Notice that oxygen is key to a combustion reaction. Propane belongs to a group of substances known as hydrocarbons. All hydrocarbons contain carbon and hydrogen, and they burn an oxygen gas to form carbon dioxide and water. A third type of reaction is the decomposition reaction. This is pretty much the opposite of a synthesis reaction. Synthesis adds things together, decomposition breaks them apart. In a decomposition reaction, you have a single compound that breaks down to form two or more substances. Generically, we can show it like this. AX breaks down to form A plus X. Decomposition reactions often require energy to start, such as by adding light or heat or electricity. To illustrate this, let's go back to the fume hood so we can see a decomposition reaction at work. This is an example of a decomposition reaction. This is the decomposition of ammonium nitrate, which can be kind of unstable. As we heat the ammonium nitrate, we see that it begins to decompose. We can actually see the vapors forming. These vapors are N2O, otherwise known as nitrous oxide, and water vapor. This is actually somewhat of a low temperature decomposition. Ammonium nitrate can decompose at a higher temperature, but does so explosively, forming nitrogen gas and oxygen gas as well as water vapor. Again, though, this is an example of decomposition, where you have one compound that breaks down to form two or more substances. The last two types of reactions are what we call replacement reactions. Sometimes they're also called exchange reactions. The first is what we call a single replacement reaction, and the second, a double replacement reaction. Let's talk first about the single replacement reaction. During a single replacement reaction, the atoms of one element replace the atoms of another element in the compound. We could generically see it this way. If we have substance A reacting with substance BX, then we would have products AX plus B. You see how the A and B switch positions there? Here's an example of a single replacement reaction, the reaction of sodium and water. In this reaction, the sodium actually replaces a hydrogen in the water and forms sodium hydroxide. The other product is hydrogen gas. You can see how one element, sodium, replaces another element, hydrogen. Single replacement. Here's a single replacement reaction involving zinc metal and hydrochloric acid. Let me put this in the flask. You can see that gas is evolving. That is hydrogen gas. So the zinc has replaced the hydrogen in the hydrochloric acid, forming zinc chloride solution and hydrogen gas. It's important to note that in a single replacement reaction, metals will replace other metals, or they may replace hydrogen. They don't replace nonmetals. Here's another example of a single replacement reaction, the reaction of copper with silver nitrate. Here the copper will replace the silver in the silver nitrate, and we'll have the product copper nitrate with silver left over. In order for a single replacement reaction to take place, though, the metal that's by itself has to be more reactive than the metal that's in the compound. So how do we know which metal is more reactive than another? We do this by means of what we call the activity series. The activity series is sort of a list of the pecking order, or king of the mountain. The ones that are closest to the top of the list are the most reactive, and those are the ones that will do better at a single replacement reaction. Notice that near the top we have our group 1 metals, and some group 2 metals as well. And you might recall that those are the most reactive of our metals. In fact, those metals at the top of the list are so reactive they can replace a hydrogen in water. However, once we get past sodium, those metals are no longer reactive enough to take a hydrogen away from water. They are, however, reactive enough to replace hydrogen in an acid, since acids are pretty reactive anyway. So as we go further down the list, the less reactive these metals are. And as you can see toward the bottom of the list, ones like silver and platinum, and especially gold, those are going to be the least reactive metals on our activity series. So how does this work? Take, for example, the reaction between lithium and zinc chloride. Will a reaction occur between those two substances? And the answer is yes. The reason is because lithium is very reactive. Lithium will replace the zinc and form lithium chloride with leftover solid zinc as a byproduct. Poor zinc. Oh well. However, if we try this the other way, in other words, if we try to get zinc to react with lithium chloride, there's no reaction. Zinc is not as active as lithium is, and therefore is unable to replace lithium in lithium chloride. No reaction occurs in this case. You get the idea? So we use the activity series to decide whether or not a single replacement reaction can truly occur. How about one more example? Using the activity series, tell me if silver will react with copper nitrate. It will not. That's correct. It will not because silver is lower on the activity series than copper. And so therefore silver will not replace copper in this reaction. So no reaction occurs between those two substances. So as we stated before, in these single replacement reactions, metals only replace other metals. They don't replace nonmetals. However, a nonmetal can replace another nonmetal. Halogens, in fact, tend to be involved in this sort of thing. You can have one halogen replacing another halogen in a reaction. And we have an activity series for the halogens. Now the good thing is, it follows exactly the order you see on the periodic table, with fluorine at the top of the activity series and iodine at the bottom of the activity series. So for example, we do have a reaction between fluorine gas and sodium bromide. The result of that reaction is sodium fluoride and bromine liquid. On the other hand, we do not have a reaction between bromine liquid and sodium fluoride. No reaction occurs because the bromine isn't active enough to replace the fluorine. The last type of replacement reaction involves an exchange of ions between two compounds. We call this a double replacement reaction. Generically, we can represent it this way. If we have a reaction between the compounds AX and BY, then a double replacement reaction would result in the products AY and B, X. In this generic equation, A and B represent positively charged cations, and X and Y represent negatively charged anions. X replaces Y and Y replaces X, and that's why we call it a double replacement reaction. Remember that anions always replace other anions and cations always replace other cations. Here's another specific type of double replacement reaction involving an acid and a base. We also call this a neutralization reaction. Here we have hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base. During this reaction, we see that the chloride and the hydroxide ions change partners. So for our products, we end up having HOH, otherwise known as H2O, and NaCl, sodium chloride. So do you get that? When we put a strong acid and a strong base together, we get salt water. So whenever you put an acid and a base together, you're going to wind up with a type of salt and water, a neutralization reaction. It's important to note that there's always evidence of a double replacement reaction when one has taken place. You'll always get a product that's either a solid, in that a precipitate will form, a liquid, usually water, or you'll produce a gas. So one of those three things will always be a product when a double replacement reaction has occurred. If none of those things happen, then you don't have a double replacement reaction. We can predict whether or not a double replacement reaction will truly occur based on possible products and their solubilities. That is, how well they dissolve in water. Let's try this one. If we have a solution of sodium bromide and we combine it with a solution of potassium chloride, will a double replacement reaction occur? The answer is no. Our possible products would be sodium chloride and potassium bromide. We can look at our solubility chart to determine that sodium chloride is always soluble in water and potassium bromide is always soluble in water. Since both of these compounds dissolve completely in water, that means that there's no double replacement reaction. Here's an example of a double replacement reaction. We have two compounds. One is lead 2 nitrate and the other is potassium iodide. In this reaction, the lead and potassium change partners. Because of the strong attractive forces between the lead ion and the iodide ions, we have a yellow solid. The reactant compounds are soluble in water, and that's the reason why we don't see any kind of solid in these beakers. But when you put them together, the attractive force between the lead 2 ions and the iodide ions is so strong that the water is unable to separate them. They combine to form this beautiful yellow solid that we see suspended in this solution here. In that solution, we have the remaining potassium ions and nitrate ions that are fully soluble in water. They don't combine to form a solid. So, the interaction of lead 2 nitrate and potassium iodide is an example of a double replacement reaction. And remember, the proof of the double replacement reaction is that we'll have either a solid to form, a liquid to form, which is normally water, or a gas to form. In this case, we have a solid that forms. Here you can see the solid on the bottom of the beaker, lead 2 iodide. In the example reaction we showed in the fume hood, our two possible products were potassium nitrate and lead 2 iodide. Well, we can see from our solubility chart that potassium nitrate is soluble in water, so that's not our product. But we can see that lead 2 iodide is insoluble in water, which means that the lead 2 iodide will stay a solid even though it's in solution. That's our proof that a double replacement reaction has occurred. In the neutralization reaction we showed, water, a liquid, was our proof that a double replacement reaction has occurred. And other reactions may produce a gas, a third evidence of a double replacement reaction. That's all we're doing for this video. Today we talked about the different types of chemical reactions. We talked about synthesis reactions, combustion reactions, decomposition reactions, single replacement, and double replacement reactions. I hope this has been helpful to you, but if I can help you in any other ways, let me know. Till next time, God bless.